Module 3, Lecture B, Dictionaries and Sets. By the end of this lecture, you will be able to create dictionaries that map engineering labels to properties, values, or records. Use dictionary access and updates to manage simple project datasets. And use sets to identify unique values and detect duplicates in engineering data. Dictionary Basics. Mapping engineering labels. In engineering, dictionaries connect labels such as component IDs or sensor names directly to the data they describe, like properties or measurements. This makes information easy to organize and retrieve, much like using labels in a spreadsheet. By using labels as keys, dictionaries help engineers find specific data quickly without searching through long sequences. Dictionaries are useful in engineering because they connect meaningful project labels to related data, such as areas, materials, suppliers, voltages, or installation notes. This makes technical information easier to organize, read, and update. By clearly linking labels to their purpose, dictionaries improve both computational efficiency and human understanding in project workflows. In engineering dictionaries, each label should be unique, so every key clearly refers to one entry. Consistent names, tags, and identifiers help prevent confusion. The value attached to a label may be a simple measurement or a more detailed record, supporting the move from single data points to structured project data, organized around named objects and documented properties. Python code. Mapping engineering labels. Dictionaries link unique project identifiers to engineering information. Each key should be distinct, and its value can hold related properties or records. A dictionary is used to connect each beam label with its length in meters. Labels such as B1 and B2 identify different beams, while their stored values give the corresponding lengths, such as 6 meters or 7.5 meters. This makes it easy to look up and manage beam lengths by label. A dictionary maps engineering labels to beam lengths, so each beam can be looked up by its label. In this case, label B3 corresponds to a beam length of 5.25 meters. The example retrieves the length of beam B2 from a dictionary of beam lengths using its engineering label. It then prints a clear message showing that label and its length in meters, which helps with verification or reporting. A member records dictionary can organize structural member data by using labels like B1 and B2 as unique keys. Each label points to details for that member, such as its material and length, making complex information easy to store and retrieve. This defines a nested dictionary entry for beam B3, storing its key properties in one place. It records the beam's material as timber and its length as 5.25 meters. This structure makes it easy to access the beam's attributes later. The example retrieves the material for member B1 from a nested dictionary of engineering member records and stores it for use. It then prints a short message showing the result, which confirms that the correct value was accessed from the data structure. A new member record is added with the label B4, storing its material as steel and its length as 4.8 meters. The total number of records is then printed by using the dictionary length, giving a quick count of the labeled entries currently stored. The member records dictionary is updated so member B3 has a length of 5.4 meters. The updated value is then retrieved to confirm the dictionary now stores the correct current length. This line displays the updated length of beam B3 in meters, using the value stored after the earlier change. It gives the user quick confirmation that the beam's length has been modified. To show all labels in the member records dictionary, convert its keys into a list and print them. This displays the unique identifiers currently stored in the dictionary, giving a quick overview of the available entries. This script shows how Python dictionaries can organize engineering data for beams. It first links beam labels to lengths, then uses nested dictionaries to store both material and length for each beam. It also demonstrates retrieving a beam's material, adding a new beam, updating a length, and reporting the total records in beam labels. Mapping engineering labels. In engineering, dictionaries are useful for connecting meaningful labels to related data, such as linking a beam identifier, sensor name, or part number to its properties. They let programmers retrieve information using familiar names, which matches how engineers often discuss project data. This makes dictionaries especially effective when information is organized around named objects rather than a simple ordered list. In engineering data, a dictionary connects each unique label to a specific value. That value may be a measurement, a property, a status, or a larger set of details. This key-to-value structure makes dictionaries a clear and efficient way to organize information, because each label points directly to the data it represents. When designing a dictionary, choose labels that are stable, clear, and meaningful in the engineering context. Standardized identifiers reduce confusion and errors, whether linking drawings to revisions or samples to test results. Well-chosen labels make dictionaries easier to read, maintain, and use for accurate engineering analysis and communication. Python code. Mapping engineering labels. Dictionaries link stable labels to engineering information, making project data easier to organize and use. In this example, beam labels are connected to their materials. A beam materials dictionary maps each beam label to its material type, making project data easier to organize and reference. For example, beam B1 is assigned A992 structural steel, while beam B2 is assigned reinforced concrete. This code adds a dictionary entry that links beam label B3 to the material glulam timber. This makes it easy to look up the material for that beam and manage engineering data more efficiently. A beam can be selected by using its label as a dictionary key, such as B2. The dictionary then provides the material assigned to that beam, making it easy to look up and manage engineering data with meaningful labels. This code adds a new beam entry to the material mapping. Beam B4 is assigned to precast concrete, expanding the dataset so materials can be referenced and updated more easily as the project grows. The beam labeled B3 is being updated from glulam timber to treated glulam timber. This keeps the project data aligned with the latest material specifications. A dictionary is used to store key details about a foundation in an organized way. It records the foundation type as spread footing and its width as 2.4 meters, making the foundation's characteristics easy to access and manage. The foundation record stores a depth value of 5 feet. This lets the program retrieve the foundation depth for engineering calculations and documentation. The output summarizes key project data by first listing the available beam labels, then showing the material for beam B2 and the updated material for beam B3. It also reports that the foundation is a spread footing and gives its width in meters. This script shows how dictionaries can organize engineering data by linking beam labels to their materials for quick lookup and updates. It retrieves the material for beam B2, adds a new beam, and changes the material for beam B3. It also stores foundation details such as type, width, and depth, then prints selected beam and foundation information. Overall, it demonstrates a simple way to manage and retrieve project data efficiently. Engineering property maps. An engineering property map connects meaningful engineering labels to their specific values, much like a dictionary. This lets engineers access quantities by name, such as yield strength, instead of remembering their position in a sequence. Using familiar labels makes engineering data easier to organize, find, and use. Engineering property maps are most useful when each label points to a full record of related details, not just one value. A valve tag or sensor name can be linked to information such as its measurement range or location, helping engineers organize and interpret component data. This matches how engineering projects are managed, with each named part carrying specific properties that must be tracked accurately over time. Dictionaries are useful as property maps because they connect labels directly to their related data, making datasets easier to read, maintain, and interpret. In engineering, this helps preserve context and reduce mistakes that could lead to unsafe decisions. For example, pipe identifiers can be linked to pipe properties, and specimen labels can be linked to test results, keeping larger datasets organized and meaningful. Python code. Engineering property maps. Dictionaries make project data easier to read by connecting meaningful labels to engineering properties. Instead of counting positions, you use keys to retrieve the values you need. Create a material density dictionary to connect material names with their densities. For example, steel maps to 7,850 kilograms per cubic meter, and aluminum maps to 2,700. This makes material properties easy to access by meaningful names instead of index positions. The Material Density Dictionary is used to look up density values by material name. Steel and aluminum densities are retrieved from the dictionary, and the steel density is then printed with its unit, kilograms per cubic meter, for a clear, readable result. We add concrete to the Material Density Dictionary with a density of 2,400 kilograms per cubic meter. Then, we retrieve and print that value to confirm the new entry was stored correctly. A beam records dictionary stores structural beam data using each beam's identifier as the key. Each entry contains another dictionary with details such as the beam's span and section type. For example, B1 and B2 with their corresponding dimensions and labels. This nested structure makes it easy to organize, access, and manage information for each beam. The beam record for B1 is retrieved from the beam records dictionary using its key. This provides the beam's main details, such as its span and section, which are then printed for quick verification or use in later calculations. The beam record is updated by changing the span for beam B2 to 20 feet. The new value is then printed to confirm that the update was applied correctly and can be verified. To inspect the available data, we list the labels stored in the Material Density and Beam Records dictionaries. By viewing each dictionary's keys as a simple list, we can quickly see which materials and beams are defined without checking every entry manually. This script shows how dictionaries can organize engineering data using descriptive labels instead of position-based indexing. It stores material densities, retrieves values such as steel and aluminum, adds concrete, and then manages beam records with details like span and section type. It also demonstrates retrieving a beam record, updating a beam span, and listing available material and beam labels, highlighting dictionaries as a clear way to manage engineering properties. Updating project records. Accessing record values. In project data management, dictionaries help organize records such as engineering components or tasks by linking each field to a meaningful label. This makes values like material type or inspection status easier to find, read, and manage. Using clear labels also reduces errors when several people work with the same dataset. When working with project records, do not assume every field is present or complete. Real engineering data can be inconsistent, so missing fields may cause errors if your program expects them. Always check the data structure and distinguish between fields that are absent, empty, or contain meaningful values. Efficiently accessing record values helps engineers make informed project decisions. Clear dictionary labels make it easy to retrieve data such as inspection status, tolerances, units, and locations. This supports transparency and accuracy and prepares the way for updating records and automating reports in projects where budgets and safety matter. Python code. Accessing record values. Dictionary records can store fields for an engineering project, using clear labels to make each value easy to access. Using safe access helps avoid interruptions when expected data is missing. A bridge component record is represented as a dictionary with descriptive fields for its key attributes. It stores a unique component identifier. The material is reinforced concrete and a span of 24.5 meters. Using these named fields makes the component data easy to access and manage. This dictionary stores key details about a bridge component. It records that the inspection status needs follow-up. The load rating is 38 tons, and the last inspection was on April 12, 2026. These values make the component's information easy to access and update. The process retrieves three key details from a component record: the bridge component's unique identifier, its material type, and its inspection status. These values describe what the component is, what it is made of, and its current condition or required action, making them ready for later use or output. The code uses formatted print statements to present key details about a bridge component. It displays the component identifier, material, and inspection status in clear descriptive sentences, making the output easy to read and understand. The code gets a bridge component span in meters, converts it to feet using the standard meter to foot conversion factor, and then prints both values. The feet result is rounded to 1 decimal place to make the output easier to read. Use the dictionary get method to read the repair priority safely. If the field is missing, it returns a default value of not assigned, which avoids errors from missing data. The printed message then shows either the actual repair priority or that default value. Use the in keyword to check whether a dictionary contains a needed field, such as a load rating, in a component record. The result is a true or false value, which can be stored and then used to print a message showing whether that information is available. The code first checks whether the dictionary includes a load rating. If it does, it retrieves the rating value in tons and stores it for use. It then prints a message showing that load rating. Use the length function to count how many key value pairs are in the component record dictionary. Then print that number in a formatted message to show the total recorded fields available. This script shows how to read and work with a dictionary that stores a bridge component record. It retrieves key details such as the component ID, material, inspection status, and span, including converting the span from meters to feet. It also demonstrates safe ways to handle optional or missing fields, such as checking for a load rating before using it. Finally, it counts the total fields in the record to summarize how complete the data is. Updating field values. Dictionaries are useful for managing project records because they let you update changing information without rebuilding the whole record. Each record keeps the same field labels while only the values change, such as updating a component's status. This makes dictionaries efficient for tracking project details as data evolves. In engineering projects, updating only the needed fields in a record helps keep datasets accurate without creating duplicate records. For example, inspection or lab records may need revised ratings, actions, or measurements after new information is available. Using field names as identifiers preserves the record's context while keeping the data current and meaningful. When updating fields in a dataset, be accurate, consistent, and clear about the purpose of each change. Use the dataset's existing conventions, including standard labels and units, so records remain easy to compare. Also decide whether new values should replace old ones or preserve historical information. Careful updates help keep project data reliable as it changes over time. Python code, updating field values. Dictionaries store editable project records by pairing field labels with their current values. When a record is updated, the value changes while the label stays the same. A dictionary is created to store a bridge inspection record with each field label linked to its value. It includes a unique bridge identifier and an initial condition rating of 7. This structure makes it easy to organize and update inspection details later. These entries summarize key bridge maintenance information, the most recent inspection date, the recommended strategy of routine monitoring, and an estimated repair cost of $12,000. Together, they support condition tracking, maintenance planning, and budgeting. The code displays the current condition rating and recommended action from a bridge inspection record. This gives a quick snapshot of those values before any updates, making it easy to compare them with the results afterward. The bridge record is updated to show a condition rating of 5 and a last inspection date of June 8, 2026, reflecting the most recent assessment. The maintenance record is updated to schedule deck repairs based on the latest inspection data. The estimated repair cost is revised to $28,500, keeping the action plan and expected expenses consistent. We add a new crack width field to the bridge inspection record and set it to 3.2 millimeters. This stores an additional inspection measurement, making the record more detailed and accurate. After the bridge inspection record is updated, the code displays the new condition rating and recommended action. This quick output confirms that those fields were changed correctly. The output highlights the key bridge updates, the most recent inspection date, the estimated repair cost in US dollars, and the crack width in millimeters. Together, these details give a quick view of the bridge's condition and the actions it may require. This example shows how to update a dictionary that stores a bridge inspection record. The script first displays the original condition rating and recommended action, then changes key details such as the rating, inspection date, repair plan, and repair cost. It also adds a new crack width field, demonstrating how dictionaries can be both modified and extended. Updating records. In project data management, dictionaries make it easy to keep records up to date as work progresses. Each record can store key details such as identifiers, locations, and statuses, and these fields can be revised when inspections, maintenance, or other tasks are completed. This lets teams update project information efficiently without rebuilding the entire dataset. When updating records, distinguish between changing one field and revising the whole record. Dictionaries make it easy to modify existing values, add new information, or remove fields as engineering data becomes more complete. However, updates must be handled carefully because inconsistent field names or missing values can lead to confusion and poor decisions. Project records must be updated carefully because they often support scheduling, quality control, and shared decisions. Even small changes can affect how stakeholders understand project status or component acceptance. Updates should preserve the record's meaning, fit the data structure, and be clear about what changed and why. Done well, dictionaries become reliable tools for managing changing engineering information. Python code, updating records. Use dictionaries to update engineering records as project information changes. Careful updates help keep the dataset accurate and reliable. A dictionary is created to store a beam inspection record. It begins with the beam's unique identifier, B12, and its location, level 2. These basic details provide the starting information for adding or updating the record later. The beam record describes a 24-foot span that is still awaiting inspection. A. Patel is the responsible engineer, and the load rating has not yet been determined. The inspection date starts as none, meaning no inspection date has been recorded yet. It can be updated later once the inspection is completed and the actual date is known. The code first displays the current status of the beam inspection record, then shows the engineer assigned to it. Together, these outputs provide a quick snapshot of the record before any updates are made. The beam record is updated to show the inspection is complete with a load rating of 82.5 kips. The record also notes the inspection date as June 8, 2026, and lists M. Rivera as the responsible engineer. This code updates an existing dictionary with new project information. It adds a deflection measurement of 0.31 inches and marks the beam as approved for the next phase, keeping the record current with inspection data and status. The code safely removes an optional temporary note from the beam record using the pop method. If the field is present, it is removed. If it is missing, a default message is returned instead. This prevents errors and handles optional data smoothly. After the beam record is updated, the printed output confirms the inspection is complete and shows the revised load rating and deflection values. These results verify that the record changes were applied correctly. The code prints the value returned when a temporary dictionary field is safely removed, showing whether that field existed. It then prints the dictionary's final keys in alphabetical order, making it easier to check the updated structure. This script shows how to update a Python dictionary used as a beam inspection record. It changes existing details such as inspection status, date, engineer, and load rating, adds new fields like deflection and approval status, and safely removes a temporary field without causing an error. The final output confirms the updated values, verifies the temporary field is gone, and displays the remaining record keys. Set operations. Unique values. Sets are useful for engineering datasets because they keep only unique values and remove repeated entries. This makes them well-suited for raw sensor or log data, where duplicates are common. For example, a team could use a set to find the distinct beam material grades in a large dataset, focusing on which values appear rather than how often they occur. Sets are useful early in data exploration because they quickly reveal the unique values in a dataset. Engineers can use them to check distinct sensor IDs, failure modes, equipment models, or defect categories, and confirm that the data matches expectations. By reducing repeated entries to unique values, sets make it easier to validate engineering data and understand its structure. Use a set when you only need to know which values are present, not their order or how often they appear. This is useful for finding distinct items, such as unique pollutants in environmental data. But it will not reveal frequency, timing, or sequence. If those details matter, treat the set as a starting point and use other analysis methods to study trends or relationships. Python code, unique values. Sets are useful for keeping only unique engineering labels, but repeated records may still represent different categories. This pavement survey example shows how to inspect the data carefully so important distinctions are not lost. A list of pavement types from inspections is created, including asphalt, concrete, and gravel. Some entries repeat, which makes the list useful for identifying duplicates and analyzing the distinct pavement categories in the data. Converting the pavement classification list into a set removes duplicates automatically, leaving only the unique pavement types. This provides a simple, efficient way to identify the distinct categories in the data. To make the unique pavement classes easier to read, they are sorted alphabetically. The sorted function takes the set of unique classes and returns an ordered list, helping the data look more organized and easier to compare. Count all recorded pavement classifications to get the total number of survey records, then count the distinct classes after removing duplicates. Comparing these two numbers shows whether the original data included repeated pavement class entries. To check for repeated pavement classifications, compare the total number of records with the number of unique values. If the totals are different, at least one duplicate is present. If they match, all classifications are unique. The code summarizes the pavement survey data by first showing all recorded pavement classes, then listing the distinct classes in sorted order. It also reports the total number of records and the number of unique pavement types. By comparing these counts, it determines whether duplicate entries are present, giving a quick view of the data's variety and redundancy. This script takes pavement classification data with repeated entries, such as asphalt and concrete, and finds the distinct types by converting the list into a set. It then sorts the unique classifications and compares the number of original records with the number of unique classes to check for duplicates. Finally, it prints a short summary of the recorded classes, unique classes, counts, and whether duplicates were found. Duplicate detection. Sets are useful for finding duplicates in engineering data because they keep only unique values. By checking each new identifier, such as a serial number or sensor ID, against the set, engineers can quickly see whether it has appeared before. This helps catch possible data entry errors or other issues early, making the dataset more reliable for analysis and decisions. Sets help detect duplicates by keeping track of values already seen as data is processed. Each item is checked against the set. New items are added, while repeated ones are flagged. Because sets support fast checks, this approach works well for large records such as inspections or maintenance logs. In engineering contexts, finding duplicates helps avoid record confusion and protect traceability. Sets are useful for keeping only unique values, but that alone does not show which values were duplicated. To detect duplicates, use a set to track values already seen and record any that appear again. In engineering data, repeated values can signal problems such as mislabeled equipment or data glitches, but whether a duplicate is an error or expected still requires judgment. Python code. Duplicate detection. Sets are useful for finding repeated engineering identifiers since duplicate labels can cause confusion in a project. In this example, they are used to check for duplicate pile location IDs. A list of pile location identifiers is created from field records. Because some identifiers appear more than once, the list can be used to check for duplicates. This helps keep project documentation clear and consistent. We first count all pile identifiers, then count the unique ones by removing duplicates. A simple check confirms that the total count is not smaller than the unique count, and that at least one unique identifier exists. This helps verify the data is valid before looking more closely for duplicates. We use one set to track pile identifiers that have already appeared, and another to record any identifiers found more than once. A separate list keeps the first occurrence of each identifier in its original order, so we can identify duplicates while preserving the sequence of unique entries. To find duplicate pile identifiers, we scan through the list and keep track of identifiers we have already seen. When an identifier appears again, we record it as a duplicate. Using sets makes this process efficient and keeps the duplicate collection clear. If a pile identifier has not been seen before, it is added to the set of seen identifiers to track uniqueness. It is also added to the list of first-time identifiers, which preserves the order in which unique entries appear in the original data. The output first reports the total number of field records to show the dataset size. It then reports how many pile identifiers are unique by counting the entries after duplicates are removed. Finally, it displays the duplicate pile identifiers as a sorted list, making them easier to review. First, the program prints the pile identifiers in the order they first appeared in the project records. It then checks whether any duplicate identifiers exist, and if so, prints a message indicating that they should be reviewed. This script checks a list of pile location identifiers for duplicates. It compares the total number of records with the number of unique identifiers, then tracks which identifiers have already appeared to find repeated entries. It reports the total records, unique count, duplicates, and the identifiers in their first seen order. The goal is to flag duplicate pile locations for review and reduce confusion in the project. Common elements. Sets help engineers quickly find shared items across data sources. For example, comparing component IDs from a field survey and a maintenance schedule reveals which components appear in both. This makes it easier to confirm overlap and consistency between records like drawings, reports, and schedules without manually checking long lists. In multidisciplinary projects, teams may track different datasets, such as structural elements, repair needs, and safety risks. Comparing where these sets overlap helps identify which assets need work, which issues are urgent, and which components are both critical and maintenance priorities. Set operations make complex project data easier to interpret and support clearer decision-making. Common element analysis helps reveal important relationships in complex engineering data by checking which values belong to the same collection. It can show which design parts are available from suppliers, whether unusual sensor readings are limited to certain subsystems, or which contaminated sites are near drainage channels. Sets are useful for this because they make membership checks fast, clear, and easy to interpret. Python code. Common elements. Sets can be used to find shared engineering identifiers by comparing which items appear in more than one collection. In this example, common elements show where inspection lists overlap. A set of field survey components stores the identifiers of bridge parts inspected during a survey, such as B01 or B02. Using a set makes it easy to manage these identifiers and compare them with other groups, like components scheduled for maintenance. This is especially useful for finding shared components through set intersections. A set can store the identifiers of components scheduled for maintenance, such as B02, B04, B05, and B06. This makes it easy to compare the maintenance list with other sets like survey results and quickly find common components. In engineering work, sets are useful for tracking and matching component lists efficiently. Use the intersection operation to find bridge component identifiers that appear in both the field survey and the maintenance schedule. The result is a new set containing only the shared identifiers, helping identify components that may need attention from both inspection and maintenance teams. Sorting the common components puts shared identifiers into a predictable order. This makes the output easier to understand, especially for beginners, and keeps results consistent when comparing different runs or datasets. Count the distinct components found in the field survey and in the maintenance schedule to understand the unique items in each group. Then count the shared components that appear in both groups. This identifies which components are both observed in the field and planned for maintenance. The output summarizes component overlap between a field survey and a maintenance schedule. It reports how many unique components appear in each list, then shows the sorted components found in both. It also gives the total number of shared components, making it easy to see which items are relevant to both inspection and maintenance planning. This script compares bridge component identifiers from a field survey and a maintenance schedule to find overlaps. It identifies the components present in both sets, sorts them for readability, and reports the number of unique items in each list along with the shared count. This helps engineering teams quickly spot components that need maintenance attention. In this lecture, you learned to create dictionaries that map engineering labels to properties, values, or records. Use dictionary access and updates to manage simple project datasets. And use sets to identify unique values and detect duplicates in engineering data. In the next module, Module 4, we will go over none. Thank you for your attention. See you all in the next lecture.